The early Earth was a place of intense heat and volcanic activity. The atmosphere was a toxic mix of gases, nothing like the air we breathe today. Oceans were just beginning to form. It was a harsh and unforgiving environment, a far cry from the vibrant planet we know. Yet it was in this chaotic cauldron that life first emerged. The transition from a lifeless Earth to one teeming with life is a mystery that has captivated scientists for centuries. How did life arise from non-living matter? What were the first life forms like, and how did they survive in such extreme conditions? These are some of the most fundamental questions in science. Around 4 billion years ago, the Earth began to cool and stabilize. The first oceans formed as water vapor condensed from the atmosphere. This was a crucial step, as water is essential for life as we know it. It acts as a solvent, allowing molecules to interact and reactions to occur. The early oceans were not the tranquil blue expanses we know today. They were hot, acidic, and rich in dissolved minerals. Yet it was within this primordial soup that the building blocks of life began to assemble. Simple organic molecules such as amino acids and nucleotides formed spontaneously from inorganic matter. The earliest evidence of life on Earth comes from fossilized structures called stromatolites. These layered mounds were built by colonies of microorganisms, most likely photosynthetic bacteria, as early as 3.5 billion years ago. Stromatolites provide a glimpse into a time when life was just beginning to establish itself on Earth. Stromatolites are found in ancient rocks all over the world. They are a testament to the resilience and adaptability of life. These early microorganisms thrived in environments that would be deadly to most life today. They were able to harness energy from sunlight and convert it into chemical energy, releasing oxygen as a byproduct. By studying stromatolites and other ancient fossils, scientists are piecing together the story of early life on Earth. These fossils provide clues about the metabolism, genetics, and evolution of the first organisms. They also offer insights into the environmental conditions that existed billions of years ago. One of the most important discoveries in the study of early life was the identification of microbial fossils. These microscopic fossils preserve the remains of individual cells, providing a window into the morphology and diversity of early life. Some of these fossils date back over 3 billion years. Section 5. Life as a pioneer. Life on early Earth faced numerous challenges. The intense ultraviolet radiation from the sun would have been lethal to most organisms. The lack of an ozone layer meant that this radiation could penetrate the atmosphere and reach the surface. Early life had to find ways to protect itself. Some microorganisms evolved the ability to survive in extreme environments, such as hot springs and deep-sea hydrothermal vents. These extremophiles, as they are known, possess unique adaptations that allow them to thrive in conditions that would kill most other organisms. Section 6. The power of change. One of the most significant events in the history of life was the evolution of photosynthesis. Photosynthetic organisms such as cyanobacteria developed the ability to capture energy from sunlight and use it to convert carbon dioxide and water into sugars. This process released oxygen as a waste product. Over millions of years, the oxygen produced by photosynthesis gradually accumulated in the atmosphere. This had a profound impact on the planet. Oxygen is toxic to many anaerobic organisms, so its rise led to a major extinction event. However, it also paved the way for the evolution of more complex life forms that could utilize oxygen for respiration. Section 7. From simple to complex. The evolution of multicellular life was another major milestone. Multicellular organisms are composed of multiple cells that work together to perform specific functions. This allows for greater complexity and specialization than is possible in single-celled organisms. The first multicellular organisms likely arose from colonies of single-celled organisms that began to cooperate. Over time, these colonies evolved into more complex structures, with cells becoming specialized for different tasks. This led to the development of tissues, organs, and eventually complex organisms like plants and animals. Section 8. A universe of possibilities. The study of early life on Earth has implications that extend far beyond our own planet. By understanding how life arose and evolved here, we can gain insights into the potential for life elsewhere in the universe. If life could emerge on early Earth under such harsh conditions, then it is possible that it could have arisen on other planets as well. The search for extraterrestrial life is one of the most exciting frontiers in science. While we have yet to find definitive evidence of life beyond Earth, the discoveries we are making about our own planet's history suggest that we may not be alone in the universe. Section 9. Searching for answers. The study of early life is an ongoing process. New discoveries are constantly being made that challenge our understanding of the origins of life. As technology advances, we are able to probe deeper into the fossil record and uncover more clues about the first inhabitants of our planet. The search for answers about the dawn of life continues to inspire and intrigue scientists around the world.